This is going to be the lecture over chapter 6 and the two problems that I'm going to have for you guys to work. As it turns out, there's a third here that I'll go over, but I think it's a little more in depth than what I would ask you guys to do. But let's take a look here at the first problem. So for a cobalt 60 beam, a deflection of 57 scale divisions per minute is recorded with a 100 Rankine condenser chamber, and the full scale is going to be 100 divisions, so we're not quite there at 100%. The chamber has a calibration factor of 0.95 for cobalt 60 gamma rays that is determined at 22 degrees Celsius and 645 millimeters of mercury. So we've got our temperature and pressure. So for 100% collection efficiency and a stem correction factor of 1.02, what is the exposure rate in Rankines per minute? Now, how are we going to generate that? Well, that particular formula comes here from Kahn in section 6.11. You can see the formula right here. You can see M is going to be the chamber reading measured under equilibrium conditions and corrected for any polarity effect. N sub X is the chamber exposure calibration factor for the given quality of beam. P, TP is the temperature and pressure correction. PST is going to be the stem leakage correction, and P ion is the ion recombination correction. So the quantity X is the exposure that would be expected in air at the point of measurement in the absence of the chamber. So in other words, the correction for any perturbation produced in the beam by the presence of the chamber is inherent in the chamber calibration factor. So getting acquainted with all of that, we are again looking for the exposure rate. So factor here for M, and again, M is going to be the chamber reading measured under equilibrium conditions. So 57. We have the calibration factor here of 0.95. And again, remember that's going to take the place of this. So that's the chamber exposure calibration factor for a given quality of beam. We have our correction factor here. Now let's kind of go over that. The correction factor is going to be given by this up here. Now, you know, depending on your pressure reading, if it's kilopascals or if it's millimeters of mercury, will let you know which formula that you need to use. So in this particular case here, we are given millimeters of mercury, so we're going to go with that. 760 over P, and then we've got 273.2 plus the temperature, and then the other stuff down here. So we plug in our pressure, we plug in our temperature, and we can come up with 1.18 if we multiply all of that out. Obviously, simplify this and then simplify that. And then we just have four numbers here being multiplied and divided together. The ion combination rate here is 1. And our stem correction factor here is going to be 1.02. It's given to you. So all of that being said, all we have to do really is go through and multiply all of those numbers together. And it turns out that our exposure rate is 65.17 Rankines per minute. So for number 2, the photon flux is 10 to the 11th photons per millimeter second for a beam of photons. So 2/3 of the photons have an energy of 600 keV, and 1/3 have an energy of 1.15 MeV. So what is the energy flux of the beam? And then we'll get to the second part here a little bit later. So let's take a look here at the photon flux. So how are we going to generate this 0.78 MeV? Basically, what we're going to do is we're going to take an average. We know how many MeV we have here, and we know how many MeV we have here. 2/3 of the photons are going to be this. 1/3 of the photon is going to be this. We take an average, And that's where this particular value comes up with. Now we are going to, pardon me, multiply that here over the number of seconds, which I don't think I got to because I didn't read the second part. If the photon flux is constant over time, what is the energy fluence over a 20-second interval? So we take our energy here, we multiply it by the time. And so we have 15.6 MeV seconds. So we have this to be multiplied by the photon flux for this particular beam of photons. Multiply those two together, and we come up with 1.56 times 10 to the 12th MeV per meter squared. So what is the fluence? Well, it's going to be whatever our flux happens to be divided by the amount of time that it takes to produce that. When we do that, we come up with 7.8 times 10 to the 10 MeV per meter squared seconds. Now, the third problem here is kind of a doozy because it took me a while to kind of read through and see exactly what they were saying and where they were drawing from. The question is, the total energy absorption coefficient of air is 2.8 times 10 to the minus third meters squared per kilogram for photons of 1.0 MeV. So what are the energy and photon fluence required for an exposure of 0.03 coulombs per kilogram? All right, so we've got our energy absorption here, and that's going to be equal to, and we're going to try to gauge this with whatever the exposure rate happens to be. And this absorbed energy is going to lead us into the concept in radiation therapy physics of dose, which is going to be the energy absorbed. So right now we're working with exposure. Eventually what we want to get to is how much dose is actually absorbed in the body. Now, if we take a look here at the exposure rate, for the level of energies that we're looking at here, 33.85 electron volts per ion pair is about what you're going to produce in air. If you want to convert EV to joules, you're going to use this particular conversion factor. And if you're going to find out exactly how many coulombs of charge is produced with this, then we're going to take 1.6 times 10 to the minus 19th coulombs per ionized pair, which is the charge of the electron. So this is converting this into joules per kilogram. This is what we're going to be looking at. So now, moving on, if we take our photon fluence, or energy fluence, I'm sorry. And if you have, let's make sure I'm on it's on the beginning part of this section, this chapter. It's the previous chapter. Yes. You can see here, the fluence is going to be the change in energy over the change in area, or this is going to end up being, if it's a monoenergetic beam, it's just the number of photons times the energy that's coming through. That's sort of where this is coming from. And the units that you would end up with here is going to be the energy divided by area. And what we have here is the energy divided by the area. That's why the energy fluence here it has the same units as this. So we've got energy fluence, and this is going to end up being multiplied here by our coefficient. Now, which coefficient is this exactly? Let me see if I can point to it here precisely in the book. Remember, you have the linear attenuation coefficient, which tells you if you move in a straight line exactly how your beam is going to be attenuated. But we can take that concept and we can expand on it. we can have the energy transfer coefficient, which is going to be the average amount of energy divided by the energy of that particular wavelength, multiplied by the linear attenuation coefficient. So this this mu sub what appears to be a TR is going to be your energy transfer coefficient. It is directly related to the linear attenuation coefficient. And you also, you can take that energy transfer coefficient and you can figure out how much is absorbed and then how much is lost to bremsstrahlung. G is going to be the fraction of energy of secondary charged particles that's lost to bremsstrahlung. So if you take that out, multiply it by this, you have the energy absorption coefficient. And that's where we're coming from here. Units of this are going to be meters squared divided by kilogram. So we go through the computations here and we find out here that, back up, the total energy absorption coefficient in air is 2.8 times 10 to the minus third. That's what we're going to end up with right here. So if we want to figure out what this rate here is, and again, remember, if we go back, sorry for jumping around all over the place, but I'd rather you know what we're talking about. The fluence rate of the energy flux, the intensity. If we take that and we divide it by the exposure rate, we end up with 33.85 divided by this particular value here, which again, oops, it's going to be the energy absorption coefficient. So if we take that, divide it by that, I came up with 12,100 when I did it. I'm not exactly sure where they got the 12.6 from. But here, if we go forward and find phi, which, let me see if I can find, there we go. Phi divided by the exposure rate, this would be 12.1 divided by all of this times the energy here of this monoenergetic beam. You would come up with something close to this. Again, I couldn't quite compute this particular number, but I think the rest of this is pretty well sound. So that question is a little bit more involved, which is why I'm not going to ask you of it. I'm just going to ask you these first two.